I have a fairly new topic that sort of emerged in the last few years, and about phase transitions and critical states in monitored quantum systems, and especially monitored quantum circuits of the type that people use for quantum applications in quantum information. This work was done with, most of the work I'll talk about was done with a student at Berkeley, Yimu Bao, and a postdoc, Soonwon Choi, who's since then moved to, as a faculty member to MIT, and a more younger graduate student, Zach, who also did some of the work that I'm going to talk about. I might get towards the end to some work done also with Maxwell Bloch, another graduate student in Berkeley. So by way of introduction, I want to make a distinction between how classical systems thermalize, or how we imagine thermalization in ideal classical systems, although we know that really all systems are quantum, but classical systems thermalize in a way that maybe is kind of more familiar. We start from some initial state, the system just runs forward in time, but because of chaos, if I sample the state, I can look at the state in some intervals. And if I look at the state at some intervals, it looks like a completely random state. So classical thermalization is basically randomization of the state, but it's important to understand that this state you see, if you take a snapshot, and the snapshot means you can, for example, read all the particle positions and the particle momenta, then you have the full information about the state, and then you can go on and evolve it, but all the information encoded in that state is available to you when you look at it, and it's all encoded locally, namely in the particle coordinates and velocities or momenta. Right, this is in the right-hand side is another depiction of classical thermalization in the form of a distribution that kind of becomes more and more complex, although it takes volume and phase space that doesn't change. But the important thing is that all the information is instantaneous, can be seen instantaneous in the state, and is encoded locally. Quantum thermalization is different. So, for example, let me look at a quantum spin system where I initialize the system in a product state of the spin, so non-entangled state, and let it evolve unitarily according to some generic quantum evolution that couples the spins. Then very quickly, these spins will get entangled. And the information that may have been encoded in the initial state is now encoded highly non-locally. Looking at particular spins does not reveal any of that information. And one way to quantify the non-locality of information is to take some subsystem, I called it A here, and evaluate its entanglement with the rest of the system. Namely, you look at the von Neumann entropy from the reduced density matrix of that subsystem A. And in generic time evolution, that reduced density matrix will have an entropy that grows linearly in time, which means there is more and more information that is shared between this system and the rest of the system. And eventually it will saturate to a value that's proportional to the volume of the subsystem, which means that the information is gotten as non-local as it could be. Okay, so that's the main difference between the classical and the quantum system. If I looked at the classical spin system, maybe instead of particles, we can equate it to a classical spin system. The state becomes more and more random as a function of time from classical time evolution. But the information is still fully encoded in local spin degrees of freedom. On the other hand, in the quantum state, the information has become encoded highly non-locally. The information was completely scrambled and encoded into non-local degrees of freedom. Okay, so that's the distinction I want to make between classical and quantum thermalization. Now, there is another element, fundamental element in quantum mechanics besides unitary evolution, which is measurement. So what if we take this quantum evolution and allow people to measure, someone to measure the quantum state, an observer to measure the quantum state? Now, if the observer measures the quantum state, let's say if they could measure every qubit in the entire system at every given moment in time, they would immediately, every moment in time, collapse the state into the basis in which they measure, and it will be just a product state at every point. It will look completely classical, of course. But let's say the observer is not as observant, it's not as accurate, and it can only measure a fraction of the degrees of freedom at every given moment. But those degrees of freedom it measures will get disentangled, right? But the rest might still be entangled. And now this goes on. And the question is whether after some time, the state will effectively become classical with no non-local entanglement encoded in it. Namely, the entanglement entropy will not have a volume law form, or is that volume law form or non-local encoding stable to some amount of measurement? So that's mainly the question I want to ask, whether there is some sharp transition between classical and quantum thermalization in this system. So that's one way to phrase the question. It might sound like an esoteric question, but as I said, recently it became at least tentatively realistic to start asking such questions and testing them experimentally. An example of a really famous experiment that was done recently was the quantum supremacy experiment by Google, in which, so here is, this is the paper. So one innovation in this paper, I think, is the fact that they introduced a multiple author list, huge author list into condensed matter and low energy physics. This looks more like a particle theory, particle experimental paper. But besides that, the innovation is that in this quantum supremacy is that they, for the first time, have shown in a pretty convincing way that they have a highly non-local encoded state. So they encoded a state with highly non-local quantum correlations in it. Like I said, quantum happens in quantum thermalization. So what they did is almost what I said is going on in quantum thermalization. They took an array of qubits and started to operate on it with quantum gates. So as they operate with more and more quantum gates, the system becomes more and more non-local. And when they had a deep enough circuit, they measured all the qubits at the top, at the end of the last time. In the last time, they measured all of them. They got some string of results, and they repeated the experiments many, many times and looked at the distributions of these results and compared them to a simulation. And this comparison gave them some benchmark called the cross entropy benchmark. It doesn't matter so much what it is, but this benchmark, if it's greater than 0 here, it means that there is some non-local information still in the system. In some sense, it's sort of related to what I said about the entanglement entropy, okay? So they've shown that there is some non-local information. And now we can maybe ask the question, well, here it was a completely unitary time evolution until they've measured the state at the end. But what if there is an observer that observes part of the system or some qubits during the time evolution, whether that non-locality will be destroyed and it will immediately go to a local state, classical-like state. Okay, so what I want to say here is that these kinds of questions are already beginning to be addressed in experiments. So it's a good time to try to address them theoretically. And before I show a theoretical model that can address such questions, I want to make an important remark on what is a monitored system and how it differs from an open quantum system. Because I'm guessing that more of you are familiar with open quantum systems, systems with a bath, and with monitored systems. And sometimes there is confusion that monitored system is just one kind of open system, and it's described by somehow the same kind of maybe Lindblad time evolution, but it's not the case. I want to make a sharp distinction, at least what I call a monitored system. So a system coupled to a bath basically describes usual decoherence processes. So you have an open system, it's coupled to some environment degrees of freedom. Because it gets entangled with the environment degrees of freedom, a pure initial state will immediately become mixed. So generically, such an open system has to be described by time evolution of a density matrix. So for example, if the bath is Markovian, this time evolution is described by a Lindblad equation, or if it's discrete, it can be a Krauss map or some kind of quantum channel that is applied at each time step. Monitored quantum system are different. What happens in a monitored quantum system is really what we have in the postulates of quantum mechanics. If we initiate a system in a pure state, after the measurement result, the measurement projects the system to a pure state, okay, and to a different pure state, but the state is still pure. And then there might be another pure state. After a second measurement, it would project it to a new pure state. So the time evolution, you can think of it as a tree, and depending on the measure, and every branching of the tree is some measurement. Depending on the result of the measurement, what is the outcome, you either branch to one branch of the tree or another branch of the tree. But if you follow one branch, it's always a pure state. Okay, so the time evolution is described by an ensemble of pure state trajectories. And so in some sense, you can say, if I average over all these trajectories, if I throw out my measurement results, then I'm back to a real open system. Then really the measurement outcomes don't matter. If I'm going to average over them, then it doesn't matter that I really had the measurement outcomes. So in order for anything to be here special or different compared to a system coupled to a bath or environment degrees of freedom, the observer has to be some special entity. It has to be an entity that can process the information somehow that it gains from measurements and somehow feed it back to the problem. The way it can feed it back is by, for example, post-selection of a particular trajectory, or feeding back by actually applying unitaries, feed-forward unitaries. But somehow the information about the measurement outcomes has to be used. So I'll give you an example. If I'm interested in the properties of a typical trajectory, I'll need to repeat the measurement enough times so that the same, I have the wave function, several copies of the same trajectory wave function, so that I can take an expectation value of an observable in it, right? Otherwise, there is no way to measure an expectation value. To measure an expectation value, I have to do repeated measurements of the same state. And if I want to do repeated measurements of the same state, I need to post-select to get the same state. In order to post-select, I need to use the information of my measurements. So really a monitored system is a very special kind. Looking at the phases of monitored systems is really not only looking at, it's a phase, a collective phase of the system and the observer, which must have some capacity to process information. Any questions about this? Because I think this is kind of a crucial point to understand the whole field, I would say. So one really important message I want to say is that monitored systems are different from systems coupled to a bath or decoherence, as long as you make use some judicial use of the measurement outcomes. Okay.
Do we have any questions?
Any what?
Let me ask the question. So
yeah, sure.
In this sketch, at each measurement, it's written like you have two passes. But am I correct that because you have different possible outcomes and the degrees of freedom is very large, it's supposed to be, I don't know, many passes after each
many branches. Well, there could be, but if the degrees of freedom are just qubits, then each measurement of a qubit will give you just two possibilities. If it's a qubit, then you'll get more branching. That's right. But in the simplest case that it's just a qubit, then every measurement will give you just one branching, or just branching into two branches.
I see.
Okay.
Any other questions?
Yeah,
okay.
I just had one quick,
Sure.
Can you hear me?
Yeah.
Sorry. I just have one quick question. So I'm aware of this so-called process tensor formulation of open quantum systems, which seems sort of similar to how you've described the monitor system. I don't know if you know how it's related to that formulation.
Again, what's the name? Process tensor?
Tensor, yeah, there's a process tensor formulation of open quantum systems, which seems quite similar to what you've described.
So I don't know it. I mean, I'm not
formulating.
So far, I haven't formulated anything. I'm just kind of defined the problem. So far, I've not. I didn't give a formulation of how to treat it. It's just
sure. Yeah.
It's just the physical. The physical setup is we have measurements and we're able to, and we're conscious beings, or it doesn't matter that we're conscious, but we're able to somehow act based on the measurement outcomes that we get.
Yep.
So now I'm going to introduce a theoretical scheme, or I would say a model that would then be amenable to some theoretical analysis of this kind of system. Okay, so here is a system, model circuit that has been proved very useful. So imagine that I have a circuit of, for example, in this case, it's a linear array, one-dimensional array of qubits. Later, I'll talk about 2 dimensions where it's interesting. And we operate on it with some random 2-qubit gates. These are the boxes. And we sprinkle around as a function of going up is time, right? So, and these gates are random in space and time. So every point in time and space, we apply a different gate. And that gate could be, the simplest case is basically Haar random unitary gate, completely random on the Haar measure of the unitary group. And the measurements I sprinkle randomly, and it could be, for example, the simplest case would be just a projective measurement. So the time evolution looks like this. If in the case of unitaries, it just applies a unitary time evolution to the state. In the case of a measurement, it applies the usual Born rules, where with probability that depends on the state, I project to each one of possible measurement eigenvalues of the measurement operator. Okay, and so there is a projection and then renormalization of the wave function. This is as simple as it gets. This is just the postulates of quantum mechanics using Born rules. Now, I want to point out that there are 2 sources of randomness, maybe more, but important sources of randomness in this model. One is the fact that I'm using random unitaries. And I imagine that a single lab, for example, would have just one realization of the circuit, or at least for a measure, they would do the measurement with one realization of the circuit. They might change it later, but the randomness here is going to be useful theoretically. So I'm going to basically consider ensemble of all the possible circuits, and I will average over the randomness. But a more important source of randomness, I would say a more fundamental source of randomness, is the fact that the measurement outcomes are random. Okay, and that has to do with the random, basically the postulates of quantum mechanics, and I cannot not get rid of that source of randomness. So even in a single lab, I do the experiment many times. Almost every time I'll get a different result. Okay, so now this is a really nice model. What we want to know, for example, the simplest thing we want to know is whether there is no non-local information in the state. We imagine a very wide circuit, infinitely wide circuit if you want, and we apply the gates for infinitely long time and measurements. And we want to know in the steady state, when the system has, so to speak, thermalized, whether there is non-local information left in it. So a good measure of that would be to look at the pure states we have in each one of these trajectories, right? Each one of these branches corresponds to a pure state. So we have a branch at hand. We want to ask, what is the entanglement entropy of half the system, for example, in that branch, half the system, or bipartite entanglement with some subsystem A in that particular branch, and then average over all the possible branches, but average the entanglement entropy of the pure state over all the possible branches. And then at the end, if I have indeed a random unitary circuit, I'm going to average over all the possible circuits, the circuit ensemble. This is the last average here, So, but the important average is inside here. I'm averaging over all the possible branches here with their respective probabilities. And the branch, I denote by M. M means a certain sequence of measurement outcomes. Certain sequence of measurement outcomes corresponds to a particular state. Now I average my entanglement entropy in that particular state. And that problem has been looked at numerically first in these papers, and using different numerical schemes, and both papers found the same really exciting result, I think. And the exciting result is that there is a phase transition. So as a function of the probability of measurement, I can tune the probability in which I measure at some per gate. And as a function of this measurement probability, I have a phase transition where for weak, sufficiently infrequent measurements, my entanglement is still volume law. So it saturates to a volume law after a time of order the length of the subsystem and stays volume law. On the other hand, if I exceed the threshold rate of measurement, I get, after sufficient time, I get, and this time is of order 1, I get entanglement entropy that saturates to some order 1 value and not volume law. So there is this phase transition. Now, I want to point out that initially people looked at this phase transition in a very simple way. And that simple way is they say, well, in this circuit, I have measurements which disentangle qubits, and I have unitary gates which entangle them. So there is a competition between the disentangling measurements and the entangling unitary gates. And that competition gives rise to a phase transition. But there was a paper early on that said, oh, based on that, there cannot be a phase transition. Why there can't be a phase transition? Because if I write the rate equation for the entanglement entropy in this way, I see that at every time step, only one single unitary gate can increase the entanglement. It's only the unitary gate that acts on the boundary of the system, of the subsystem A, right? Only that unitary gate can increase the entanglement of A. Others can easily be shown to not touch the entanglement of A. On the other hand, at every moment, every time step, I measure n times p measurement qubits, And so I disentangle order n qubits. So my entanglement should grow by order log 2 and decrease by order n, which is the entire system size. So of course, this is no contest. And according to this paper, entanglement, the measurements should always win, and eventually at some time that's not so, it doesn't scale with system size even, decrease the entanglement to 0 or to some area law. But this, yeah.
I think, could we interrupt you? We have a question from Ehud. Please,
sure. Yes.
Please just go ahead.
Yes, thank you. I was wondering, just when you introduced this model, now how is this model specifically different from an open quantum system? Because it seems like you're averaging over everything as you would.
Excellent. Excellent question. Excellent question. I will show that more explicitly in about 3 transparencies, but what I'm averaging over is the entanglement entropy, which is nonlinear in the density matrix of the state at that particular point in time. So if I averaged first over the density matrix and got the average density matrix, that would be the same as the open system. But since this is a nonlinear object in the density matrix, the entanglement entropy, it's completely different from an open system.
All right.
That really measures the typical behavior in single trajectories.
Okay, thank you.
Yeah, I'll come back to that in a minute. Thanks for the question.
Right. So I also have a question. So
sure.
Am I correct that there is, one could think, is as a competition between surface and bulk physics, because one term is proportional to the area and another is proportional to the volume?
Well, okay, so this argument is wrong. So I want to say this argument here is not correct. So the argument is, and I'm going to say what the fallacy is. So actually, the first paper we published on this was to show why this argument is not correct and what does enable a phase transition in this case. So this argument was based on the inaccurate concept that there is some competition between entangling and disentangling here. But the competition actually is much more interesting. The competition, I'm not going to go deeply into it. I'm going to show how it comes out in a statistical mechanics model. But one can also show it in terms of information theoretic quantities. What is going on here is really that, let's forget about the measurements for a second and ask what the unitary gates are doing. The unitary gates are scrambling the information or scrambling the state and making it more and more non-local. When the state is non-local, information about the correlations between the subsystem A and the subsystem B become more and more non-local, so that when we measure a qubit, a local qubit, we don't reveal information about correlations between A and B. And so although we disentangle that qubit, since we don't reveal any information about the correlations between subsystem A and subsystem B, the entanglement between A and B doesn't change. So the fallacy is that really measurements are not required to change the entanglement entropy by order n, and in fact, if you scramble the information sufficiently, they can have absolutely no effect on the entanglement between the two subsystems. So they disentangle that particular qubit, but disentangling that particular qubit has essentially zero effect on the entanglement between subsystem A and B. So the main point is that the scrambling of information hides information and protects it from being revealed by measurement. So really, it tells you that there is an emergent error correcting code due to the scrambling of the information. There is an emergent quantum error correcting code, and that is what ensures the robustness of the large-scale volume law entanglement. And only when you degrade this protection enough, you have a critical point towards an area law state. Okay, actually, yeah. So my outline is probably I will get mainly to the first part, and second part maybe a little bit kind of give you a taste of the last part. But most importantly, I want to give the basics, which is the nice thing that this kind of emergent error correcting code has a very, very nice description in terms of a statistical mechanics model, that once you have it, you can predict a lot of other phenomena very nicely and intuitively. So I want to mainly concentrate on the statistical mechanics model and what it means. So before getting into that, I want to, that's related to something, to talk about something related to what Joachim asked me a minute ago, which is how to characterize the ensemble of trajectories. So the usual way we characterize the quantum state is to take the expectation value of an observable. In this case, that would mean taking the average over all the measurement trajectories, and then maybe at the end also average over the unitary gates. But if I do that, it's really basically constructing an average density matrix and calculating the trace of this operator in the average density matrix. So I might as well just evolve this average density matrix, which would be open system dynamics. But again, as I said, this can immediately be seen that at least in this setup is trivial. The reason it's trivial in this setup is because the measurement operators are all Hermitian. The quantum channel I'll create in this way will be unital. So at long times, I'll just get the unit matrix. So there could not be any phase transitions that I can see in this way. Okay, I need to do something else, both theoretically and experimentally. I have to somehow use the measurement outcomes to post-select in order to see a phase transition. So at least I need to consider fluctuations over trajectories which are encoded in second moment. So instead of looking at the expectation value of operator in the state and then averaging over the state, I can look at the expectation value of that operator squared or to some power, and then average over all the possible measurement trajectories. That's a second moment observable. And an example of such a second moment observable is simply the purity, right? The purity has the density matrix twice. So instead, in this case, the purity O is sort of, okay, it's a strange operator, but but it gives you the simplest second moment quantity, which is the purity of the state. And here you see I'm averaging over all the measurement outcomes. And rho m is the unnormalized projected state. So it's not, I need the denominator in order to normalize. Now, all these higher moments can be captured in a simple way. I can capture them as first moments, like averages, usual averages, if I construct an object which is n copies of the density matrix. So if I have n copies of the density matrix, I can construct these moments as simple averages, but now it's a generalized density matrices, which is really a many copies. And there is subtlety that if I want to correctly average over this PMs, and because of this denominator, one can see that in the end I have to take some replica limit. I can't stay with n copies. In the end, I have to take the limit of just a single copy, but first do all the calculations with n copies. So this is maybe for the experts, and you can ask me about it later, but I'm going to, for now, put it aside and imagine that I'm doing the calculations for n copies of the density matrix, right? What you see here is just density matrix of a pure state, because as I told you, I can deal with pure states. Density matrix of a pure state multiplied n times. It looks trivial, right? But I'm going to look at the dynamics of that thing. Okay, so I'm interested in the dynamics of that thing when I apply measurements and random unitaries. Now, before looking at what it gives, let's try to understand the symmetries of the system. There is because I'm looking at n copies, there is an intrinsic symmetry in the system. And moreover, there is a special symmetry that is special for the case where I have only measurements and unitary evolution, no decoherence. So what is special about having only measurements and unitary evolution is that it keeps the purity of the state, right? So it preserves the purity of the state. What does this symmetry correspond to in terms of this n copy density matrix? Well, you can see it really with your eyes. If you have n copies of a pure state, all of them are the same, right? All the cats are the same, all the bras are the same. These are the global states, right? So I can take this, I can take the cats and permute them as I want, and I'll still have the same state. And I can take all the bras and permute them, and I'll still have the same state. This is a global permutation symmetry of left permutations and right permutations corresponding to the bras and the cats. And there is another symmetry associated with the fact that this density matrix remains Hermitian. And so it's a semi-direct product with some Z2 symmetry. Actually, it's a time reversal-like Z2 symmetry associated with complex conjugation and transposing, right? Sending ket to bra. Okay, so and important to note that this symmetry, this permutation symmetry, left permutation symmetry, let's call it, is broken when I introduce the decoherence, because decoherence sort of entangles the ket and the bra, right? When you have decoherence, you get a mixed state, and the mixed state is a sum over eigenvalues, so it becomes locally a sum over these psi m's, and so it entangles ket and bra, and you can no longer permute. It really likes the special permutation, which is I will call the identity permutation. It locks you into the identity permutation. Okay, so now how do I calculate such a, for the simplest non-linear observable, which I showed you, is the purity, which is interesting because it's related to the entanglement entropy. So let's look at how we would calculate the purity. In order to calculate the purity, since it's a second moment, it's trace of rho squared, I'll need the two copies of the density matrix. So I start with two copies of the density matrix. It's two copies of the initial state, basically ket bra. And then I evolve them in time. So I have to reproduce my unitary gates 4 times because I have a forward evolution for the ket, backward evolution for the bra, forward, backward. So it's U star, U star. It's U star and U, not U dagger, because I really want to look at the ket as at the bra as a ket and evolve it forward in time. And that takes U dagger to U star. That's it. So I have basically 2 copies, but each copy is made of U and U star. So I have these 4 circuits, 4 identical circuits. And in addition, I have measurements that are drawn here in red. And all the measurements in all the copies, I have exactly the same measurement outcomes that come out. Okay, so this is basically the circuit I want, and I can represent it because I can represent this circuit that evolves this double density matrix as a tensor network, and as a tensor network. And in the end, I need to calculate. Sorry, one important thing. In the end, I need to calculate the purity. How do I calculate the purity? First, I need to trace over the B subsystem to get rho of A, and tracing is marked by these rainbows here, by these connections here. This tracing simply identifies, right? Tracing identifies degrees of freedom in the ket and the bra here. Identifies ket and bra and sums over them, okay? And then next I have to multiply rho A by rho A. So this is matrix multiplication. That identifies degrees of freedom of the bra in copy 1 and the ket in copy 2. I call that swap because, look, instead of identifying degrees of freedom in the same copy, I need to identify them in opposite copies in the subsystem A. And in this tensor network representation, you see I represented here that A has different boundary conditions at the top of the network, which correspond to swap of two subsystems, and the subsystem B corresponds to the identity. So I call it the identity because if I'll have more than two copies, then A will be some cyclic permutation in order to multiply rho A by rho A n times, and B will still be the identity permutation. Each copy is connected to itself. Okay, so I have a boundary condition, I have a nice tensor network, but it's impossible to calculate. Calculating that for a particular set of unitaries is just as hard as calculating the dynamics problem, so I don't know how to do it. How can I do it? How can I simplify this problem? Well, remember that each one of these boxes correspond to 4 unitaries put on top of each other. And now I want to do an average. Now let me average over the ensemble of circuits. So after calculating the purity, now I want to average over the ensemble of circuits. So I need to average over the unitary U times U star times U times U star. If I do that, it turns out that this projects me to, while I have many possible outcome states, because I have, for example, I have many qubits coming in and many qubits coming out because it's a quadrupled system. This averaging, for a reason that actually is very intuitive, projects you only onto 2 possible states. And the 2 possible states, which I'll call, because there are 2 possible states, let me call them spin up and spin down. They're the states where you identify the ket and the bra in all the copies, the ket and the bra of the same copy, or you identify ket and bra of different copies. Why is that happening? So if I average over the unitary, I get some average phases from the forward and backward evolution. Ket and bra evolution is basically forward and backward evolution. If I evolve forward and backward, I get random phases. And by averaging, I'm going to kill the contributions that have a random phase, and only the contributions with no random phase remain. Which ones are those? Those are the ones where the forward and backward time evolution are exactly the same. So, but here I have 2 possibilities to do that, because I have 2 forward evolutions that are identical and 2 backward evolutions that are identical. So I can identify the paths, right? The evolutions are the same, but I'm looking at quantum mechanics, so there's many different paths I can take. So if I identify the path of the forward and backward evolution in the same copy, I call that a spin up. If I identify the forward and backward evolution in different copies, then I call that a spin down. That's the only degree of freedom I have now. So I've mapped this contraction of the tensor network to summing over all the possible configurations of these classical spins. And it turns out that they have, these different configurations have different weights that behave like the weights of a ferromagnetic Ising model in this special case of 2 copies. Okay, so we have Ising, calculating this tensor network is basically the same as calculating the partition function of 2-dimensional Ising model. 2-dimensional because 1 dimension is the time and 1 dimension is this network space, the space of the qubits. And the average, so we get basically a ferromagnetic Ising model. And there are special boundary conditions at the top of this Ising model. And the boundary conditions are, as I told you, the B subsystem forces you to have the identity permutation, which I called spin up. And you're forced to have the downspin, which is the swap permutation in the subsystem A. So you force a domain wall through the top of the system between A and B. And now if you ask what is the free energy of this domain wall, well, okay, we'll see what the free energy of this domain wall means. I just want to generalize. Now we looked at the situation where we have 2 copies. In general, if we have n copies, then subsystem B will still force the identity permutation. Subsystem A will enforce a cyclic permutation, and each spin could be in any permutation. It could correspond to any one of the n factorial permutations, each spin. Okay, so that's in this case, for n copies, it'll be a statistical mechanics model, ferromagnetic statistical mechanics model with symmetry Sn, or Sn cross Sn. Any questions? Maybe after this, actually, there might be, and even if you didn't follow the details, it doesn't matter. The idea is that, well, whenever I calculate the quantum dynamics of something, I can represent it formally as a tensor network. Now, if I average over the unitaries that made up this tensor network, and it turns out also in average over the measurements that made up this unitary network, what I get is is a sum, is like a partition sum. The degrees of freedom correspond to the only degrees of freedom left act like some classical spins, and I have a classical ferromagnetic model. The entanglement entropy, which is the log of the partition function, is basically the entanglement entropy associated with introducing a domain wall into the system, forcing a domain wall into the system. Now, you know that the Ising model has 2 phases. In one phase, it's ferromagnetic. It's in a ferromagnetic state, in which case, in low temperature phase, it's ferromagnetic state. And then domain wall would cost a linear free energy. That's exactly the volume law phase. In terms of the entanglement entropy, it's order L. It's the volume law phase. In the paramagnet, it would cost a constant energy, and that would be the area law phase. Okay, so it's very easy to understand that in the case of 2 copies, one can generalize this and take the replica limit, and it's still, at least each one of the phases is easy to understand. It's not so easy to understand the phase transition, but I'll not discuss it now, right now. I want to give another. So far, I looked at one way to look at it, at the entanglement entropy, which is telling us whether there is or isn't non-local information, how non-local the information inside the circuit is. So I've taken the perspective of the circuit. I want to understand this transition from another perspective now, which is the perspective of the observer. So the observer gets measurement outcomes. And the question is, how much information, how much can they learn from these measurement outcomes? For example, suppose I have a state, and in my initial state, I do my experiments one day, I run the experiment many, many times, and I get a distribution of measurement outcomes, which is this probability distribution P naught. The next day, I want to do it again, but without me noticing, a graduate student came into my lab and changed my initial state by applying a small unitary on one of the qubits. This unitary is e to the I theta xj times psi naught, for example, right? They rotated one of my qubits, so encoded some information. And now I do the same experiment. I run it many, many times, but with that new initial state. And the question is whether, if I look at my distribution today, I'll be able to distinguish it from the one I had yesterday and know and gain information about this change in initial state. Okay, and this can be I can quantify that by because now I'm a classical observer and I have just classical measurements outcomes. I can look at the information in them, at the divergence of the information in them using the KL divergence, which is very useful, for example, in statistical analysis, machine learning. I can look at the KL divergence between these 2 distributions. And if I take the Taylor expansion of this with respect to this angle theta, it looks at the coefficient of theta squared is called the Fisher information. It's basically quantifying how much information I can gain about small changes in the initial state. So this object, the Fisher information, I can map that to the same statistical mechanics model, it turns out, except the boundary conditions are different. The boundary conditions are basically all spins up in the top, oops. All the spins in the top are up, not half up, half down. And the Fisher information is, somehow it ran away. The Fisher information is basically telling me, is mapped to 1 minus the magnetization of at the spin at the site where the perturbation has been done. So what should I expect? If it's in a ferromagnetic state, then that magnetization is non-zero, or maybe even close to 1, close to the maximum, in which case I have missing information compared to the maximum information I can gain from measurements about the initial state. On the other hand, in the paramagnetic state, although the top of my system has spin up, that boundary condition decays exponentially into the bulk, and at the bottom of the system, the spin doesn't know about it, and it has zero polarization. So at the bottom of the system, after long time evolution, I'll have zero magnetization, sigma equal to 0, which means that this Fisher information will be maximal. So the phase transition in terms of the Fisher information is it's a phase transition between a situation where after making enough measurements, I can gain the maximal possible information I can gain about the initial state is if I've measured all the spins right after the measurements has been done, or in the other phase, the volume law phase, I'll have some missing information. And this missing information is telling me that the circuit is effectively hiding information from me. So this is again the emergent error correcting code that is hiding information and thereby protecting it from measurements. I guess how much time do I have? Maybe 10 minutes. I can't hear you.
So officially it is 3 minutes, but we will be happy to continue.
Okay, maybe I'll just go to one last point, which will be a few minutes. But maybe if there are some questions on this, I can answer questions now. Continue a little bit.
Do you have any questions? Please just go ahead. I have a quite generic question.
Yeah.
When we have phase transitions, we usually have strong fluctuations in the vicinity of the phase transition.
Yeah.
In the critical regime, for example, critical series. Is these ideas related to such system in the vicinity of transition between these two regimes?
Yeah. So I didn't. Right.
Critical.
Yeah. Yeah. I deliberately steered away from discussing the transition itself here. It's actually an open question. What is the transition? But yes, there are definitely strong fluctuations. You can measure many quantities that behave like CFT. So it behaves like a CFT. And you can show that it behaves like a CFT, but that CFT is actually quite complicated, and because it's obtained in some. Here I'm looking at Ising spins, but the actual CFT is not. So naively, I have an Ising transition. So all the fluctuations are fluctuations of an Ising critical point, but that's not correct because I haven't taken the replica limit, which I should, to do everything correctly, I need to take the replica limit. And then one can show that there is a weird phase transition, that a weird CFT that has to be central charge 1, central charge 0, like percolation, but it cannot be percolation. So it's not clear what exactly are the fluctuations, critical fluctuations. People don't have a good handle on the critical point yet of this problem. But there certainly are critical fluctuations.
Also, I have missed, is it a Ising model at 0 temperature or at finite temperatures?
Finite temperature.
What places?
The mapping is to a classical Ising model at some finite temperature.
But what plays the role of the temperature?
Well, the measurements play the role of temperature, more or less. The measurements actually play the role of temperature, but more than that. So if you just look at the Ising model, yes, they play the role of measurements of temperature, but they also introduce this effective disorder. If you actually take the replica limit, you have to understand them as also introducing disorder. Actually, I'll get to it in 2 slides. Yeah. So without measurements, the system is sort of trivial, and it has only energy and no entropy, unless you have you force the domain wall in such a way that gives you some degeneracy of how it could go energetically, and then there are some entropic fluctuations. But roughly speaking, it's at 0 temperature when you have no measurements, and it's finite temperature when there are measurements.
Thank you.
Yeah. And measure a sufficiently large number of measurements, you drive a transition to the paramagnetic state.
I see.
Okay, but this is not a good description of the transition. You need to actually take the replica limit properly, and it's not, and then you get the transition that we don't understand. Okay, but yeah, here I was going to say something about the difference between a purely unitary circuit and a circuit with measurements. So one can, derive this kind of statistical mechanics model, which is much simpler in this case, has been derived for the case of no measurements, just unitary gates, in which case the domain walls between you force a domain wall between a cyclic permutation and identity permutation, and that domain wall has to follow straight 45-degree angles in this case. And the reason is, the deep reason is because of the light cone constraint that you have in unitary dynamics, and you can see it in the statistical mechanics model simply because you don't have entropic term, and you have you basically get the minimum energy configuration in this way. And if you calculate the entanglement entropy in this case, it's just the domain wall free energy, and the domain wall has no fluctuations. You get just L. You just get volume law with no maximal volume law, maximal possible volume law with no fluctuations, no subleading term. On the other hand, if you look at the model with measurements, not only do you have temperature, but actually more importantly, it introduces effective disorder. So now the domain wall actually tries to minimize its free energy by going through as many measurements as possible. And this completely changes its dynamics. And it, instead of bulging order L like a pyramid into the bulk, it bulges only order 2/3, and it gives you it still gives a volume law because it has to go over some order L to cut some order L bonds. But in addition to this order L part, there is subleading L to the 1/3 term. Okay, so. But it's hard to see because it's a subleading term. It turns out that there is an interesting way to actually see this 1/3 non-trivial exponent directly in a simple way, and it actually makes an interesting. It's an interesting physically this problem. I'll just explain that very quickly, and I think then I'll jump to my summary. So suppose I have the same system, and so far I haven't talked about decoherence at all, but real systems have decoherence. Suppose I have the same circuit with measurements and unitaries, but I also have decoherence, and to make the decoherence somehow simpler, I'm allowing only decoherence at the edge of the system. So I have an infinite path coupled to the edge of the system. That infinite path, in the statistical mechanics model, it just means I have a boundary condition at the edge, which gives me also the identity permutation at the edge. But there is an important fundamental question: how do I now quantify the entanglement? Once I have a path here, I have a mixed state dynamics. In general, my system will be in a mixed state, and then entanglement entropy, von Neumann entropy, does not really measure my intrinsic quantum entanglement. Turns out that you can measure the intrinsic entanglement in the mixed state by using a different measure called logarithmic negativity. It's a different measure of entanglement. It's a measure of mixed state entanglement, which turns out to be easy to map to the same kind of statistical mechanics model, a little bit more complicated because the boundary conditions are just different and more complicated. So instead of a single polymer, you have many interacting polymers, several interacting polymers. And the negativity turns out to be the free energy of these random directed polymers, which, because of their configuration, you have a vanishing of the volume law term. So the negativity turns out to be, the entanglement negativity turns out to be volume law, not large scale, but not volume law, L to the 1/3. So you get a critical, in the volume law phase of the entanglement entropy, if you couple an infinite path to the edge of the system, then you kill part of the entanglement, but this L to the 1/3 subleading term survives, which is kind of interesting because if I didn't have measurements, if I just had unitary gates without measurements, and I connected my system to a path at the edge, the entanglement negativity can be shown explicitly to vanish completely. So in this case, the measurements, which it previously said are disentangling, are actually acting here to enhance the entanglement of the system compared to the non-measured system. And this is a Clifford circuit simulation that shows that this analytic result indeed holds, and even in a Clifford circuit. And you get this 1/3 scaling of the negativity. Okay, so I was going to talk about one last thing. So I think I'm going to skip it. I'm just going to give you a teaser about it. So now suppose I have a 2-dimensional circuit. So a 2-dimensional array of qubits, and I evolve it in time. And let's say I don't even do any measurements. It's just like in the Google experiment. I just evolve it as a function of time for some finite time. Unlike in the Google experiment, I only evolve it for a finite time. And now I measure, I want to ask, after this finite time, did I get entanglement between the furthest away qubits in this circuit? So for example, qubit A and qubit B here that are as far as they can be, and in the limit of a thermodynamically large system, I want them to be infinite. I want to ask whether I have been able to entangle qubit A and qubit B. Now, of course, this question is meaningless if they're not in a pure state by themselves. I need to ask it only when they're in a pure state. So let me measure all the other qubits except A and B. That projects everything else into a product state, and only A and B remain in some unidentified state. And I want to ask whether there is entanglement between A and B, whether the mutual information between A and B is non-zero, or in other words, just what is the entanglement entropy of the qubit B. And it turns out, and the way to understand it through the statistical mechanics model is simple, is kind of neat. I told you that there is a statistical mechanics model that describes this 1 plus 1 dimensional system is a 2D classical statistical mechanics model. In the case where I have a 2-dimensional circuit and 1 dimension of time, I can think of it as a 3-dimensional statistical mechanics model, or if the time is, if I have continuous time, I can think of it as a 2-dimensional quantum statistical mechanics model at some finite temperature, where the time evolution is basically the density matrix of this quantum system is given by the time evolution, imaginary time evolution with some effective quantum Hamiltonian. So in this case, because we have for 2 copies, I told you we have some Ising symmetry, Z2 symmetry, the effective Hamiltonian can be easily shown to be an effective Ising Hamiltonian with some Ising symmetry. Now, an Ising system at some finite temperature would have a phase transition between ferromagnet and paramagnet. And the kind of observable that I was looking for, the mutual information between A and B, turns out to be exactly mapped to the spin-spin correlation function in this statistical mechanics model. So this is exactly mapped to the spin-spin correlation function. This means that as a function of time, the function of time becomes like a function of inverse temperature. So it's sufficiently long time, albeit sufficiently low temperature, that the system transitions to the ferromagnetic state, and I'll get an infinite correlation, spin correlation, which means I'll get entanglement between infinitely separated qubits. And that time is of order 1. So it's confusing because one would think that I need at least a time that for the light cone to connect A and B in order to entangle them, but I don't. Because of the measurements I made at the top, I don't have light cone dynamics anymore. The measurements destroyed the light cone, and I can get infinite range entanglement at some finite order 1 time, not order L time. And so there is a phase transition as a function of time at some TC where I have non-zero mutual information between A and B. And in fact, I can also turn this problem around into a problem of teleporting state that I input into A, some undefined state, unidentified state yet. I input into A and I ask if I want to read it out from B, will I have some finite overlap with the state that I encoded? And there is a phase transition where this teleportation fidelity becomes non-zero at some finite time. And all of this comes out just from the simple, from the statistical mechanics model. So here I'm trying to give some physical picture how it happens, but maybe I'm a little bit out of time. So unless I'm asked about it, I'll just go to the summary. So I showed you how to map the dynamics of quantum information to an equilibrium statistical mechanics model. This allows to predict interesting new phenomena like critical entanglement in presence of edge decoherence and finite time teleportation phase transition. And there are many outstanding open questions. What is the nature of the critical point? Can we have encoding phases and phase transitions in the presence of some bulk decoherence? And also, could we have a version of this transition that is easier to observe experimentally and does not need much post-selection? For example, can we trade post-selection for feedback? And finally, can we utilize some of the insights gained in understanding these transitions to design better quantum error correcting codes? So this is it. So thanks. Take questions.
Yes, let's thank Ehud for a very nice talk. Do we have any questions? Please just go ahead. I have a question. So a bit maybe technical. So there are two models. Yes, so there is this qubits with gates, and there is statistical mechanics for spins. How are they connected? So is there any transformation like duality? So you could step by step model to another, or they're connected in a different way?
It's not duality because it's not duality. It's simply connected by the fact that if you contract the tensor network, so they're not equivalent. They're equivalent models only after averaging over unitaries, right? So you need to average over the ensemble of circuits, and once you average, you map to, in this averaged system, you map the model to a statistical mechanics model, and the statistical mechanics model simply comes out as a contraction of this tensor network. The contraction of the tensor network has some free internal parameters associated, or variables associated with it, and you have to sum over all their possible configurations, and that is what gives you a statistical mechanics model. Now, the problem is that this statistical mechanics model is not one stat mech model. In reality, I told you, as I said, in order to actually capture the averaging correctly with the measurement outcomes, averages over measurement outcomes, you actually need to take some limit of, you have to look at all the statistical mechanics model for all the number of replicas, and then at the end take the replica limit n equals 1. So there is, it's more similar, I would say, to disordered models, where you can map a disordered model into an effective stat mech model, maybe after averaging over disorder. So in that sense, maybe it's similar, but it's not a duality between the quantum dynamics and the statistical mechanics model. I think, but there is an explicit mapping. So we have a paper that actually where we actually do the mapping. Where is it? Here. I mean, these two papers that we appeared back to back, we actually explicitly developed this mapping from, and I showed you what different quantities in the mapped statistical mechanics model are related to in the information dynamics, like the Fisher information and the entanglement entropy, and also the negativity. They're all related to some specific structures in the statistical mechanics model.
Okay, so could I think about like, so because you have qubits, each qubit corresponds to the spin 1/2, so you have two states for the.
It's not each qubit; it's each unitary. Actually, is strictly speaking, each unitary has two spin 1/2s. But never mind. In the end, you can integrate it out, and each unitary is related to a spin 1/2.
So not spin, but this unitary evolution corresponds to the.
Yeah, the unitary at the point where there was a random unitary gate is replaced by a spin 1/2 degree of freedom.
Oh, I see. But I thought they have been placed not regularly, but randomly.
No. They're replaced regularly. If it's a regular lattice of regular brick wall circuit, you replace it everywhere by spin 1/2s.
So if you miss one, for example, one unitary gate, in that case, you will have a spin system with defects. So spin will be missing. So can one?
Yeah, if your network structure is different, yeah, there will be a missing spin. There will be, yeah, you can design different networks if your unitary gates are not everywhere, right?
Different defects, so domain walls. I don't know. Okay.
Yeah. Yeah, you can design some lattice defects if you want. Yeah, that's right.
Okay.
That's right.
Thank you. Any other questions?
Yeah, hi, this is Joachim again. Very nice talk. I really enjoyed this. Thank you very much. So I have, a simple question. And so if I understand correctly, you're describing this phase transition where you have an emergent area law, and you call this an error correcting code or emergent error correcting code. Can you maybe—
Where there is a volume law, not where there is an area law. Yeah, where there is a volume law. Yeah, yeah.
Where there is, oh, okay. So yeah, anyway, but can you maybe briefly explain in how far this leads to error correction?
Okay.
Can it correct random errors, or can it only correct errors that you put in there by these measurements?
Oh, good. Yes, absolutely. Right. So yes, that's an excellent question. So it can only correct, or I would say it's not exactly an error correcting code in the sense that it's an error protection code, I would say, because it protects from errors. It retains the information in presence of these errors, but we don't have an algorithm to decode it. So it's not a useful error correcting code. So that's one thing. And the second thing is directly related to what you asked. And the kind of errors it protects from are only these measurements and not usual errors, which would be like decoherence. So decoherence will come in as some magnetic field in the up direction, and it will destroy the phase transition, and everything will be a non-error correcting phase in the presence of decoherence. So that's true. So in the presence of decoherence, at least in this simple case, there is no protection. You might be able to enhance the protection by using some feedback. And then, so I didn't talk about this, but there is this SN cross SN symmetry is broken by the decoherence, but it's not completely broken. There is still residual symmetry, Z2 symmetry. And if you manage to add some feedback terms that would disfavor the state, the trivial state, the state where you, the identity state that the decoherence likes, then you could still have a transition, an Ising transition, and into an error correcting state that protects against real errors. But we don't know how to do that and whether at all it can be achieved. So in principle, there is still an opening for that. But for any kind of simple decoherence, it's not protecting against that for now.
All right, thank you very much.
Thank you. Any other questions?
Yes, I guess I have. I think it's a very nice question, but I will ask you.
Sure.
Thank you for your talk. I was wondering, so is there a, okay, could you comment on experiment? Is there a connection with some experiment? Can your theory prediction be tested in some laboratory or in Google, or can this be tested in other systems?
Yeah, sure. So let me say, first of all, let me say why it's very hard, and second, why maybe you can. So, so the reason it's hard is, again, because you require post-selection. And post-selection is hard. You need to have in your hand several copies, not many, but several copies of the same state. And to get the same measurement outcome is exponentially rare, right? So that's why you can't do it in a very big system. You can do it in a small system. So that's one reason why it's hard. There is one reason why you can make one direction where you can maybe get it is I described this phase transition in the teleportation fidelity at finite time. In this case, you need to make measurements, and there is a version of this also in a one-dimensional array. And in this case, you need to make measurements only at the top. So you don't need to make measurements in the bulk of the circuit. So you need less post-selection than in the measurement-induced transition. And the phase transition is very, very closely related. So in this example, you can map from one to the other. So, but you still need a lot of post-selection. So, and at the critical point itself, to do good finite size scaling, you need to go to larger and larger systems, and probably it's not going to be feasible. What maybe is possible is that if you have more structure in your system, it turns out that you can have, and that's another paper I didn't talk about, that we had with, you can have not only area law and volume law phases, but you can have many volume law and many area law phases, some of them quite exotic and have different, different information properties. And because if you're not going to focus on the phase transition, but just classify the different phases with an experiment, the different phases could have a very short correlation length, which means that with a fairly small system where you can do, you can even do post-selection because it's not small, you can, because it's a small system, you can characterize these different phases, but not the phase transitions. So the fact that you can have different phases in a quantum circuit like that, I think is possible. If these phases have a short correlation length, you can, it's enough to look at a 20 qubit circuit, and you can show that it exists in that 20 qubit or 30 qubit system, and it's reasonable to do post-selection on these 30 qubits. So in this case, it's probably possible. So to emphasize it again, it's probably impossible to capture the measurement-induced phase transition, but it's possible to classify the different and show that you have different phases. And so that's one thing. There is now another question, whether instead of doing post-selection, one can replace it by some kind of feedback and see a very similar phase transition without need of post-selection, but just doing feedback based on the measurement outcomes. If we find an algorithm to do that, then it will be easy to do these experiments in Google's platform. But meanwhile, Google is trying to do the experiment that I talked about at the end, which is this finite time teleportation fidelity phase transition. That's something that they at least are setting up to do. Let's hope that it's not going to have unexpected complications, but this is probably possible to do.
Okay, I think thanks very much for your clarification. Thank you.
Thank you. Any other questions? Just go ahead. If no, let's the speaker again. Thank you, Ehud, for a very nice talk. And
okay, bye. Thank you.
bye. See everybody in a month.
Bye.